Hello everyone, and welcome to today's video. Today we're going to take a look at section 7.1, what is stoichiometry? So stoichiometry can be defined as the study of quantitative relationships among the amounts of reactants used and the amounts of products that can form in a chemical reaction. So a balanced chemical equation is going to be essential for making these calculations and predictions related to these quantities in a chemical reaction. So we're going to use these coefficients in the balanced chemical equation as our mole ratios. So this mole ratio is the ratio of the amount in moles of any two substances in the balanced chemical equation. Let's take a look at an example here of a turkey sandwich. So this illustration shows that for every one turkey sandwich, you need two toast slices, two turkey slices, one lettuce leaf, and one tomato slice. So these reactants, you can kind of think about it, has a 2 to 2 to 1 to 1 ratio that will produce one sandwich. So just thinking about this, how much of each ingredient would you need to make 4 turkey sandwiches? Well, for these 2 toast slices, we're going to take these 2, times it by 4, which is going to give us 8 that we need. These 2 turkey slices, we're going to take those 2 times by 4, which is also going to be 8. We need 1 lettuce leaf for 1, so we're going to times this by 4. So we need 4 lettuce leaves, and the 1 tomato slice, we're going to also multiply by 4, and we're going to get 4 tomato slices. So we need 8 slices of toast, 2 turkey slices, 1 lettuce leaf, and 1 tomato slice to give us 4 sandwiches. Okay, so our focus on today is going to be looking at these ratios of these reactants and products. So if we're going to consider the following chemical equation of 2H2 gas plus O2 yields 2H2O gas, here we have sort of a visual representation of what this looks like. So at the microscopic level, looking at these particles in particular, we have 2 molecules of hydrogen gas that combine with 1 molecule of oxygen gas to produce, this is actually 2 molecules of water. Okay, so 2 molecules of hydrogen gas for every 1 molecule of oxygen gas yields 2 molecules of H2O. At the macroscopic level, we're going to be using moles as, again, this quantity, this amount. So that is where we use these coefficients in our balanced chemical equation. So here, because there's nothing there, you know that there's an invisible 1. So at this at the macroscopic level, we have for every 2 moles of hydrogen combined with 1 mole of oxygen gas, and again this produces 2 moles of water. Okay, so in these next couple of examples, we're going to be converting from moles of one substance to another. Okay, so solving some problems using these mole ratios. This is where we can predict, theoretically, how much reactants we need or how much products we can produce. So in this first example, we want to know how many moles of oxygen gas are required to react with 5 moles of magnesium metal. So how you can think about this is identifying the given and required quantities. So we know we have 5.0 moles of magnesium. We are interested in finding how many moles of oxygen gas do we need. So our mole ratio here in this case is looking at our coefficients. You can see we have a 2, an invisible 1, and a 2 right here. So if we're comparing magnesium and oxygen together, we can see for magnesium that for every 2 moles of magnesium, we have 1 mole of oxygen. So if we were to solve this problem, we're going to start off with the required information. So we are interested in finding out how many moles of oxygen do we need. We know we have 5 moles of magnesium, and we're going to multiply this by our molar ratio. How I like to start these is we are looking to cancel these moles of magnesium. So that's what's going to go on the bottom. We are interested in finding the moles of O2, of oxygen. So from here, okay, the values that we substitute, we are going to get from our balanced chemical equation. So for the moles of O2, we can see there's an invisible 1. For the moles of magnesium, you can see we have the coefficient of 2. When you put this in your calculator, you take the 5, make sure to include these sets of brackets, and you know you've done this correctly because these moles of magnesium will cancel with these, and you're left with the moles of oxygen, which is exactly what we are looking for. When you do this calculation, you are going to get 2.5 moles of O2. So the format and how you can kind of treat this is at the start here, this is what is required. This is what you're looking for. Then you typically write what is given to you, and we multiply this by the mole ratio, which we get from our balanced chemical equation. Okay, so how many moles of magnesium oxide can be produced from 12 moles of oxygen gas? So in this particular case, we are given 12 moles of oxygen gas, which is O2. We are looking for the moles of magnesium oxide in our particular question. So we can see this is already balanced. We have our 2, we have the invisible 1, and a 2 right here. So our mole ratio comparing oxygen and magnesium oxide is that for every mole of O2, you can see there's the invisible 1. We have, looking at magnesium oxide, 2 moles of MgO. So we are looking for the moles of magnesium oxide. We are given the information of 12 moles of O2. So we can times this by our molar ratio now. Again, I want to cancel these moles of O2, and I want the moles of MgO. Before putting any values in, you can see that these moles of O2 are going to cancel with this, and we are left with exactly these moles of MgO. So now we just have to input our values. The moles of MgO we can see is that coefficient of 2, and the moles of O2 we can see is that invisible 1. After we multiply this, we are going to get 24 moles of magnesium oxide. So as a problem solving hint, always double check the units and make sure you are writing your units every single time, and that will make your questions much easier to try. And then again, ensure your answer is reasonable. Always try to do your calculations twice. So looking at the mass relationships, the mole ratio can only be obtained from the coefficients in a balanced chemical equation. So that must always be your first step. But these mole ratios do not apply to the masses. So the mass of one chemical substance cannot be calculated directly from the mass of another. We must convert to moles first. So the strategy here that we'll do in just a second, let's say you are given the mass of one substance. You need to divide by the molar mass to get the moles of substance A. Then we can apply our molar ratios, and that will give us the moles of substance B. Timesing it by the molar mass will give us the mass of substance B. So as we looked a little bit before, the moles is sort of the bridge in finding information. So let's take a look at an example now on how we actually do that. So we are interested in finding what mass of hydrogen gas is necessary to react completely with 50 grams of nitrogen gas. So the first thing we have to do is write a balanced chemical equation. There are 2 nitrogen here, so we need to put a 2 in front here to balance that. So 2 nitrogen, 2 nitrogen. There's 2 hydrogen. There are 6, 3 times 2, 6 hydrogen here. So on this side, we're going to go ahead and add a 3 to have it balanced. So next you want to identify the given and required information. So underneath your balanced chemical equation, we'll just rewrite that here. To help you organize your solution, over on the left-hand side here, we can kind of put some key variables. So we're going to put our moles, our mass, and our molar mass. This is how we can stay nice and organized. Our question tells us, or it asks us, what mass of hydrogen gas is necessary? So across from the M underneath the hydrogen gas, we're going to put this X. We know we have 50.0 grams of nitrogen gas. Okay, so we can see you have this value here. We're interested in finding the mass of this. So the first one we're going to do is convert this given mass to moles. You know the molar mass of this N2 is going to be 2 nitrogen. So if you take 2 multiplied by 14.01, you're going to get 28.01 grams per mole. Okay, so the first thing we can do is find these moles given this mass and molar mass. So our moles of N2, and please always make sure you're writing your subscripts, is the mass of N2 divided by the molar mass of N2. So that's going to be our 50 grams divided by 28.0 grams per mole. And we're going to get 1.78 moles. So that's what we can input right here. Another piece of information that we can find is the molar mass of H2. Remember from your previous unit, you only look at the compound itself when you're finding the molar mass. These coefficients, this invisible 1, this 3, this 2, is used for one thing and one thing only. It is finding these molar ratios. We do not use these coefficients to calculate the molar mass. So what we're interested here is the molar mass of H2. Since there's 2 hydrogen, we do 2 multiplied by 1.01, and you're going to get 2.02 grams per mole. So what we can do now in step 4 is using these coefficients from the balanced chemical equation, we can determine the mole ratio and use the mole to find these missing moles of the hydrogen here. So writing out your ratio, for every 1 mole of N2, we have 3 moles of H2, of hydrogen. We are not interested in NH3 in this particular example, so we're just going to focus on these 2 reactants. And so to find the X mole of H2, what are we given? Well, we just calculated 1.78 moles of N2, and we're going to multiply this by the molar ratio. I want to cancel my units of N2, and I want my moles of H2. So that's how we know we can write in this orientation. Without even putting any numbers, we know this and this are going to cancel. The moles of H2, we can see, is this 3, and N2 is that invisible 1 right there. When we calculate this, you are going to get 5.34 moles of H2. So we can sub that in your little chart as a visual representation of what information you have. So the last thing is, you can see we have our moles, we have our molar mass, and we can easily calculate the mass of our H2. Okay, so we're going to convert the moles to the required mass. So the mass of H2 is equal to your moles of H2 multiplied by your mass of H2. Remember your triangle, you have N, M, and M right here. Okay? We know our moles of H2, we just calculated, is 5.34. Your molar mass of H2 is just 2 hydrogen, which is 2.02 grams per mole. You multiply this and you're going to get to 3 significant digits, 10.8 grams. You can include a therefore statement or put a nice little rectangle around it. Okay, we round this to 3 sig digs because our 50.0 is also to 3 significant figures. So now let's try one more problem, again, on this process. So we are interested in finding what mass of aluminum chloride, so that's our AlCl3, can be produced from the reaction of 60.0 grams of aluminum metal. Okay, so we can start off our equation. You have your N, your M, and M. Okay, so what information do we have? We have 60 grams of aluminum metal, and we want to find what mass of aluminum chloride. So this is going to be your focus, our aluminum and our aluminum chloride. Looking at the periodic table, our aluminum has a molar mass of 26.98 grams per mole. Our aluminum chloride has 1 aluminum plus 3 chlorine. So that is going to be 133.33 grams per mole. So you can sort of see the process right now. If we find these moles using our molar ratio, which we'll just do in 2 seconds, then we can find the moles of our AlCl3 and calculate our missing X. So the next step we must always do is balance our chemical equation. So here we're going to put a 2 for aluminum. We have a 6, we have a 2, and we have a 3. So our first step is going to be to find these moles of aluminum using our mass and our molar mass. Okay? And we're going to be utilizing our triangle, moles, mass, and molar mass. So our first step, we need to find our moles of aluminum. To do that, we take our mass of aluminum divided by the molar mass of aluminum. Our mass given to us in our question was 60.0 grams. The molar mass of aluminum, as you can see, we are not using the coefficients. They are only used in the molar ratio. So the molar mass of aluminum, looking at your periodic table, is 26.98 grams per mole. When you divide these, you're going to get to 3 sig digs, 2.22 moles. Okay, so we have our moles of aluminum. Now we can use our molar ratio between aluminum and aluminum chloride to find our missing moles here. So our step 2, we want the X moles of AlCl3. We know we have 2.22 moles of aluminum, and now I want to cancel my moles of aluminum, and I want my moles of AlCl3. So now to fill in these values, let's take a look at our balanced chemical equation. For aluminum, we have the value of 2. For AlCl3, we have the coefficient of 2 as well. We know we did this correctly because these moles of aluminum will cancel with these moles, and we're left with moles of AlCl3. When you do this calculation, you will get, again, the same thing of 2.22 moles of AlCl3. So here we have our number of moles. So our final step now is calculating our missing mass. So here we want to find the mass of AlCl3, so the theoretical mass that we can produce of this product. So we are going to take the moles of AlCl3 multiplied by the molar mass of AlCl3. That is going to be our 2.22 moles. Again, the molar mass of 1 aluminum, 3 chlorine, we get 133.33 grams per mole. Showing our units, we know the mole and mole will cancel, and we're left with our grams. Excellent. Rounding this, as you can see, to 3 significant figures, you are going to get the mass of 296 grams. So we can sort of just finish off our final answer, putting our variable back, putting a nice rectangle around this so the answer is nice and clear. And again, we have this to 3 significant figures. So that concludes our lesson for today. Thank you all for watching.